Hello everyone, I'm Mirko Ravanelli, and in this brief video I would like to present my recent work on learning speaker representations with mutual information. And this is going to be basically the same presentation I recently gave at Interspeech 2019. Well, let me first of all say that deep learning is all about learning good representations. In fact, whatever is the learning modality, supervised, unsupervised, self-supervised, or whatever is the specific application of deep learning, NLP, computer vision, or speech, in all these cases, deep learning is about learning good hierarchical representations that are able to describe in a very robust and efficient way our input signals. In the community, we have seen a recent trend towards learning these representations using mutual information. And this is especially true in the field of computer vision using the so-called self-supervised learning. But what is mutual information? The mutual information between two random variables x and y is defined as the KL divergence between the joint distribution of these two random variables and their product of the product of their marginal distributions. What does it mean? In practice, if there is a strong relationship between these variables, the mutual information is very high, and if there is no relation between these variables, the mutual information is equal to 0. So why mutual information is so attractive? Basically, one good thing of mutual information is that mutual information can capture not only linear relationship between random variables, such as correlation, but can also capture complex nonlinear relationship between these random variables. And this is something really very powerful. But unfortunately, due to this double integral, mutual information is very difficult to compute in high dimensional spaces. Fortunately, a recent work called MINE, Mutual Information Neural Estimation, found that it's possible to maximize, minimize, or even estimate the mutual information within a framework that closely resembles that of GANs. So how MINE works? First of all, we draw a batch of samples from the joint distribution, and we call these positive samples. And we will describe during the presentation how we can draw samples from the joint distribution. Then we draw a batch of samples from the marginal distributions, and we call these negative samples. Again, we will describe later how we can draw these kind of samples. And then we feed these samples into a special neural network. This special neural network is trained to maximize the Donsker-Varadan bound of mutual information. So the Donsker-Varadan bound of mutual information is a lower bound on MI, and if we train the parameter of our neural network such that we maximize this lower bound, at the end we will eventually estimate the true value of mutual information. So note here that the idea is really very clever. So first of all, the authors have defined a lower bound of mutual information. Then they have parameterized this lower bound using an artificial neural network, and then they have maximized this lower bound to finally estimate the mutual information. Okay, but how can we use MINE? MINE can be used to learn good representation, like in the context of the recently proposed deep InfoMax technique. Deep InfoMax has been used for in the context of computer vision and is based on maximizing the mutual information between a local and a global representation of an image. So here the basic idea is to have a local representation that also is also aware of the global content of the image. This is another very interesting idea, and if you would like um, to hear more details, you can read the paper referenced here. In the literature, there are also some attempts to learn mutual information based representation in the context of audio. One example is the constructive predictive coding work proposed by DeepMind researchers. And here, the idea is to maximize the mutual information between current and future representations. And here, the idea is to have local features which are predictable about the future. And as you can see from the paper referenced here, the author are able to learn very interesting representation using this simple technique. Well, the technique that I'm gonna present in this video is inspired by the recent works on motion information and has the main goal of learning good speaker representations. I mean, representations, features that embeds speaker identities. And we called our technique local InfoMax to highlight the fact that we only use local information only. So what is the basic idea behind local InfoMax? Let's assume to have a speech sentence. Here the underlying assumption is that we have only one speaker in a speech sentence. And let's assume to take two random chunks within this sentence. Once we have randomly sampled these chunks, we can encode these samples using a neural encoder that hopefully provides a representation that highlights speaker information. In practice, in the context of local InfoMax, we would like to maximize the mutual information between two representations corresponding to two random chunks of speech sampled within the same sentence. Why this could highlight speaker identities? Well, first of all, we have to consider that one reliable factor that it is shared across random chunks is clearly the speaker identity. If we randomly sample just two chunks within a sentence, the speaker identity is for sure the same. And in this way, we should be able to disentangle this constant factor from other variable factors that characterize the speech signal, for instance, phonemes. Okay, but how can we maximize this mutual information? As you can see, the game that we finally play is really very simple. First of all, we choose a random chunk from a random sentence and we call it anchor chunk. Then we choose another random chunk from the same sentence and we call it positive chunk. Note that it's called positive because we expect a kind of relationship between the positive and the anchor chunks. Then we choose another random chunk from another random sentence that likely belongs to a different speaker, and we call this chunk negative chunk because we don't expect any kind of a relationship between the negative chunk and the other two anchor and positive chunks. Then we convert this sequence of samples into a higher level representation using a neural encoder that give us a ZA, ZP, and ZN. After that, we can combine these samples to form positive and negative samples. Positive samples are the concatenation between the anchor representation and the positive representation. And note that positive samples can be seen as samples drawn by the joint distribution. Then we form also negative sample by concatenating the anchor representation and the negative representation. And these are negative samples that can be seen as drawn by the product of marginal distribution. Then we feed these samples into a discriminator. And basically, the discriminator here should figure out if in input we have a positive or a negative sample, or in a similar way, if the two inputs that are in inputs are from the same speaker or from two different speakers. Well, depending on the loss that we use for our discriminator, we may have different ways to maximize mutual information. One possibility is to use the mind objective that we have mentioned before. One other possibility is to use InfoMax, which is the objective used in the context of the constructive predictive coding paper mentioned before. Note that mind and InfoMax are very related. One other possibility is to use binary cross-entropy as discriminator loss. If we use binary cross-entropy, we are not maximizing the KL divergence between these two distributions, but we are maximizing the junction divergence between these distributions. So it's not the exact definition of mutual information, but still something very related that can capture non-linear and meaningful relationship between random variables. One important remark is that the encoder and the discriminator are jointly trained, and the game we play is not adversarial. We are playing a cooperative game because the encoder and the discriminator should cooperate together to find a good speaker representation. So this is a key difference between this approach and GAN, for instance, where we have adversarial neural networks. Once we have trained our representation using this approach, we can plug this representation into a standard supervised speaker recognition system, such as a speaker ID classifier or a speaker verification system. Let me also say a few more words on the encoder. You may find many details on the paper, but our encoder is a convolutional neural network based on SyncNet. Well, some of you may have noticed some kind of similarity between a local InfoMax and triplet loss. In fact, in both frameworks, we basically maximize the distance between positive and negative samples. So what is the main difference? The main difference is that in triplet loss, we rely on Euclidean distance, while in local InfoMax, we rely on mutual information, which is a very powerful and meaningful measure of distance, which is actually not even a measure of distance, is a measure of divergence between distributions that can also capture very complex non-linear relationship between random variables. So the first experiment that I would like to show you is a speaker identification experiment on LibreSpeech, where we compare different different losses. Note that libre speech is not probably the best task for speaker identification, because even though we have a lot of speaker at the end, um, the task is very simple, but at least we can see a relative comparison between the losses. In the table here, the first line shows the results we have achieved with triple loss, and then we have mutual information based losses such as mine, info NC, and finally the binary cross entropy. So from the table you can see that mutual information losses, mine, info NC, NBCE, and binary cross entropy outperform triple loss, validating our idea that we need um, more meaningful measure of divergence between positive and negative samples. If you compare mutual information losses, we can see that at the end, the best performance is achieved with binary cross entropy. According to my experience on this, we have seen that binary cross entropy is easier to optimize because it's bounded, and when we approach zero, we basically have we converge basically. While with mine and info and C, we have some kind of unbounded. We have a growing metric, for instance, with mine, and it's very difficult to decide where and when to stop. So at the end, binary cross entropy is better. I don't think there is a theoretical reason for that, but it's just because it's it's easier to optimize. Okay, let me show you some more results. Here on the left, you can see some speaker identification results on a reverberated version of libre speech. Here, to add more complexity, we have convolved each sentence of libre speech with a different impulse responses, with the goal of adding complexity due to the introduction of acoustic reverberation and also a channel effect. The table reports the results, the classification error rates in three different settings. The first row shows the result that we have obtained using a fully supervised system in which we have an encoder and a speaker ID classifier in a pipeline, but we are not pre-training our encoder with limb representation. So this is basically a simple end-to-end system that doesn't take any benefit from local InfoMax. The second and the third row shows some results using local InfoMax, and note that we can use local InfoMax in two different ways. One way is called frozen, in which we basically pre-train our encoder with the limb representation. We freeze this representation before feeding the speaker declassifier. So in this way, the encoder is basically used as a kind of feature extractor. But we can use also our encoder in a different way, because we can pre-train the encoder with a representation, local InfoMax based representation, and we can fine-tune both the encoder and the speaker ID classifier during the supervised training phase. So this is called limb fine-tuning. And as you can see, this gives some performance benefits. So it's very convenient to use local InfoMax in this setting. On the right, you can see some speaker verification results on Moxlab. As you can see from the equal error rate results, it's you notice that local InfoMax provides a pretty good performance that outperforms well-known systems such as GMM UBM, iVectors plus PLDA, CNN plus triple loss, and we finally achieve an equal error rate of 5.8, which is something reasonable, but not the best performance obtained in the literature. For instance, the X vector CALDI gives us an equal error rate of 3.1%, but the X vector of CALDI are trained on augmented versions of VoxLab 1 and VoxLab 2, so it's not really comparable. So even though in the literature you can find better results, I think these techniques provide at least a very interesting starting point. First of all, because it is very simple, it is based on raw samples directly, and also during the unsupervised training phase, where we train the limb representation, we are not explicitly using any speaker labels at all. So I'm pretty sure that there are um, huge margin of improvement using local InfoMax, maybe just training with more data, working a little bit on the encoder architecture, and maybe using PLDA at some point to improve the performance. Okay, conclusions. In this brief presentation, we have introduced local InfoMax, which is a technique based on mutual information to learn speaker representations. And we have seen that LIM is able to highlight very high quality speaker representations, and the technique is efficient, simple of course, but also very efficient because it is based on local information only. The advantage of having local information only is that we can parallelize a lot and train our neural network in a very efficient way. The issue with local InfoMax is that the representations that we learn are very task specific. So this representation works very well for speaker identification, but they are not working at all for speech recognition, for instance, because we are not learning phoneme-based representation. To improve this aspect, we already have done a work called problem agnostic speech encoder, which is described in this paper and will be object of another video, in which we have trained at the same time multiple self-supervised tasks with the goal of learning a kind of universal speech representation. So take a read into this paper or see this video on this channel for further information about this new idea. That's all. Thank you very much for your attention.